All right, so we're recording. I'm going to do some problem solving. We're just going to go through some of the exercises, not all of them, but a good chunk of them. All right, so at the start of week 3, we were looking at dual spaces, right? So you pluck out a particular finite dimensional vector space. Let me reduce my audio here. Be better. So you look at a finite dimensional vector space, and you construct from it the dual space, saying, okay, what are the basis vectors? I'm going to build something for each basis vector that just sends that basis vector to 1 and sends all the other ones to 0. So I call the function that sends E1 to 1, I call that E1 star, right? So in this nomenclature, it looks like this with J replaced with 1. And you just have a little star up here, and that denotes the dual to E1. You have the same thing for E2 and so on, and those EJ stars form a basis for the dual space V star. So we want to show that that's a vector space. Okay. So exercise 1 is, let me do this. So we write V is a vector space. Well, I guess it's not a vector space, I can't write. V is a vector space, and it's spanned by E1 through En. And we'll say it's real, right? So you have real numbers times, or real linear combinations of these things. E1, E2, up through En. And you form V star to be the span of E1 star, E2 star, up through En star. And the idea is that you want to show that this is a vector space, right? Of course, I mean, kind of, almost obviously is, but we need to actually check that this forms a basis. Is it the full exercise? Yeah. Oops. So I should get, I should firstly be able to show that every linear function, so let's say like f is a linear function, so we write that as Hom sub r, mapping from V to the real numbers. I should be able to say that this lives in V star, right? So how can I express f as a linear combination of the basis vectors in V star if I have that it lives in here, right? So it's a linear function, so what does that mean? It means that f eats things, namely that look like this, a1, e1, plus a2, e2, plus dot dot dot, plus an, en. Right, so vectors living in V. And it spits out something in agreement with this, a1, f e1, plus a2, f e2, plus dot dot dot, plus an, f en. And each one of these is a real number. Just the f of ei's. Okay. And then you take a linear combination of those real numbers and you get a real number at the end. Let's see. So how can I express f as one of these? Well, I want f to be equal to some kind of linear combination. So f should be equal to, let's say, c1 times e1 star, right? Because I'm taking linear combinations of the ej stars to get elements of v star. So if I want to show that f lives in here, then I need to show that it's a linear combination of these things. Plus c2 e2 star plus dot 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 plus cn e n star. And I just need to find out what the cij's are. Right, so what is c1, what is c2, what is cn, and so on. Well, I know how f acts on vectors in V, so why don't I just let this thing act on vectors in V and see if that gives me any hints. Right, so you might say that I have f a e1 plus dot 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 plus an, so that's a1, en. Well, this should be the same as doing this, c1 e1 star plus dot 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 plus cn en star. And then you plug in a1 e1 plus dot 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 plus an en. Okay? And that should be whatever this number is up here. But also, because I'm plugging in something into a sum of these ci, ei star things, or cj, ej star things, I should be able to just apply this to each one of these e's linearly. So this ends up being equal to c1, e1 star. And then you plug in all of the stuff that you're plugging in over here, just to that one part. an en, and then you have the second e2 star, and then so on up through cn en star, a1 e1 plus dot 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 plus an en. Okay. And then these things act linearly, so you can distribute. So you end up getting c1 e1 star times a1 e1. You can actually pull this outside. That becomes c1 a1. And that eats e1. I'm going to distribute all these other terms. Plus dot 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 plus, what is it, cn, or sorry, c1 an e1 star en. But note this is 0 because of how the e stars act. Right? They spit out 0 if you plug in any of the other basis vectors besides e1. So all of these are 0 actually. You're just left with that. And then you have plus dot dot dot, and the same thing happens over here. Everything except the en part dies. So this is what's left over. So then you have a n en star en, and namely these are 1 by definition of the dual. So you end up getting c1 a1 plus dot 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 plus cn an, and you want this to equal this thing up here. So the idea here is that you just let ci equal f of ei. So we say, okay, we want this to equal a1 f e1 plus dot 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 plus an f en. So just define the c's so that you satisfy this, and then you're done. This equality checks out. So I wanted this to be the case, and now this makes it so. So that gives you that you can express any linear function mapping from V to real numbers. So any linear functional on V, you can express that in the dual of V, in the dual space. It's a covector. Now, let's see. As a byproduct of defining V star to just be the span of these things, as long as they're linearly independent, you have that this is a basis for a vector space, and taking the span of that makes it into a vector space. So all that has to be done is to check that these are linearly independent. And so how you do that is you say, okay, take a linear combination of them, c1 e1 star plus c2 e2 star plus dot 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 plus cn en star, set it equal to 0, and then you want to show that the only way for this to be the case is if all the ci's are 0 themselves. So this should be 0, this should be 0, this should be 0, all separately. Right, so we want to show that. So how you would do this is you would say, okay, you can do the following. You can show that you can subtract. So I have this equation being true to start with, and I want to show that this implies that all the ci's are 0. So I can reword this equation a little bit by saying c1 e1 star could be considered to be negative, and then you have on the other side. So I'm just subtracting c1 e1 star from both sides. Okay. Now, note, let's see. Note how this acts on e1. This is just negative c1, right? Because this is just 1. But what that means is that this thing has to eat e1 and produce negative c1. So c2 e2 star plus dot 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 plus cn en star, plugging in e1 should be equal to negative c1. But we know that because there's no e1 in here and everything else is just ei, where the I is not 1, this is 0. So what that means is that c1 is negative 0 or c1 is 0. Repeating this argument, putting in particular negative ci ei star ei on the left side, and then this of course is negative ci. This thing evaluates on the other end as c1 e1 star plus dot 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 plus ci minus 1 ei minus 1 star plus ci plus 1 ei plus 1 star. So you're just skipping over the ei plus dot 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 plus cn en star, plugging in ei is 0, And so automatically you get that Ci is 0 for all I. Okay. So we got that by virtue of knowing how these Ei stars act on the basis vectors Ei for V. And that tells us that this is a basis for a vector space. And so if I form the span of that basis, it is going to give me a vector space. Okay. So that is the solution for number 1.
That was a cool proof.
Thank you. I didn't know if that was going to work. I just went for it. Normally, when you're showing something as a vector space, you take two elements and you show that adding them together gives you another element of that space. But because you're taking the span, that's like a completion. So as long as you have linear independence, you're good.
So that also shows that they have the same dimension?
It does not, but because the bases are the same cardinality, you have that for free. Right, so I have n many basis vectors both in V and in V star. So I did show that in the the EI stars for V star, E1 star through En star do form a basis. So there's a V star is n-dimensional. Now this actually fails if you're working in the case that V is infinite dimensional. You won't get the same. You won't get an isomorphism between V and V star, I should say. I do forget which direction that fails in. I would imagine it fails in the direction of V acting more like a direct sum. I might be wrong about that. I think the dual is going to be more restricted in the case where you have infinite dimensional vector spaces. Maybe not. Exercise 1 and 2 are done. Okay. 2 was actually covered by what we just did. Okay, so what is 3? I think this was a long one, so that might be the one I skipped. So what is it saying? It's saying you put an inner product on a vector space. That's defined to be a function that satisfies right linearity, so it's bilinear by virtue of symmetry, and it's also positive definite. So if you plug in something against itself, you get a quadratic form, which has to be positive, or 0 if you plugged in 0. And then the exercise is to show that an inner product on an arbitrary finite dimensional vector space V admits a basis for V, so that the corresponding dual map is defined by sending V to its left pre-multiplication. So what is that doing? You take an inner product, and you want to find a basis for V that sends vectors to covectors that act like left multiplying with themselves. Can't do that one off the top of my head. I would have to think about that for a couple minutes. May come back to it. We'll see. Okay, this one's computational. So exercise 4. So this is number 4.1. Show negative y dx plus x dy. Plugging in the radial tangent vector field. So that's x del x plus y del y. This should be 0. Okay, so to do this, you just, well, does anybody remember how I multiply these things? Or how I evaluate differential forms on tangent vectors? So namely, this lives in sections of T star M, which is cotangent bundle, and this lives in the sections on the tangent bundle. Okay. So you can abuse linearity. Right, so you break up into the components, and you say, all right, this should be negative y dx, plugging in x del x plus y del y, and then plus x. So that's just this part being evaluated on this. And now you evaluate the other term, which is this on the tangent vector field. So x dy evaluated on x del x plus y dy del y. Okay. So that's equal to the thing we're trying to show is 0. Now, you can just use this and think of it as a selector for this only. Or you could, do the proper algebraic thing and say, well, dx distributes, right? Because we have a sum here, a linear combination. So that becomes x dx del x plus y dx del y. Of course, this one's going to be 0 because dx and del y don't go together and give you anything. And this just gives you 1. And then the other side you can do faster, right? So it's plus xy dy del y. So you just get xy out. This ends up being negative yx plus xy, which is 0, and you're done. So not too bad. Couple more. This one's cosine y dx minus sine x dy. Cosine x, wait, is it y dx? Minus sine x dy. And then you plug in something. What was it? Sine x del x. Cosine y del y. And that should be 0, I think. Right, so proof. Okay. So this part is not going to act on this because the bases don't agree. So they're acting like selector functions. So you just get cosine x, sine x, for this term and this term together. And then this one only likes the other term, so you end up getting minus sine x cosine x equals 0. Done. One liner. And finally, this is actually precisely the same thing as this. But if you aren't used to thinking of differential forms and tangent vector fields as being matrices, it's a good exercise to actually compute it directly. So we want to show cosine y, so this is the dx component, and sine x, which is the dy component, multiplies with sine x, which is the del x component, cosine y, which is the del y component, should give you 0 as a result. Okay. Proof. Of course, you end up taking this one, and this one, and this one, and this one, so this ends up being like a dot product. So these two go together, and these two go together. So that's cosine y, sine x, and I've written something wrong. Minus sine x cosine y. And again, same thing here, cosine y in both cases. This should be 0. Oh. So you can work with matrices or you can just write out the components. It's more natural a lot of times to write out the components because you're thinking about what the actual objects you're working with are. You know, the fact that they're sections of a bundle, so they're living everywhere at different points over a manifold, is made more clear by looking at this kind of thing than just thinking of a matrix with like functions as the components. Okay, so that was exercise 4. Okay. What about 5? So let f of x equal x. Compute df in terms of basis 1 forms. So you're living on R, right? It's a map from R to R. And in fact, if you are, this doesn't have to be just from R to R. It could be, does, and you can't think of it any other way. I was going to say, like, you could think of it as a map from R50 to R, but then, you know, you'd be actually writing x1, x2, so on, through x50, and saying this is just x1. And then the exterior derivative is similarly easy to compute. It's just that, you know, I didn't write that here. The argument is only 1, so it necessarily is a function from R to R. And so by that omission, or admission, we should have that this is a map from the tangent space on R to the tangent space on R, okay? Or tangent bundle. So df in particular is going to be del f, del its only component, or its only argument, dx. Okay? And del f del x is just 1. That ends up just being dx. Okay. So that's it. 6. This one is a little nicer. Wait. Oh, come on. It's x cubed sine y over z. And namely, this is a map from R3 to R. So df for us should be a map from the tangent bundle over R3 to the tangent bundle over R. Each of which, the tangent bundle over R3 looks just like the tangent spaces at every point in R3 look just like R3 itself. Because if you think, okay, I've got three directions, X, Y, Z. You look at a particular point in 3D space here, maybe it projects down to this position. And you think, okay, what are the directions I can go in? Well, you have del X, you have del Y, you have del Z. Well, locally, I need to make these infinitesimal, but the idea is still present visually. This looks like R3. So the tangent space to a point, so call this P, tangent space to a point of R3 is isomorphic as a vector space to R3. Right? It looks exactly the same. It's only when you introduce some kind of weird like curvature in your manifold that this ceases to be the case. You'll have something like TP of a 3 manifold is isomorphic to R3 still, but it won't be the case that that this still looks like M. M won't even have any vector space structure. It'll just be a manifold. So you can't say anything like this in general. That doesn't make any sense. Okay. Yeah, so actually computing this thing, we want to get df. So you just differentiate with respect to x, and you get 3x squared, and then this other stuff's left over, y over z, dx, that's what I differentiated with respect to, plus, and then you differentiate with respect to y, so you end up getting x cubed over z by chain rule, cosine y over z dy. And then finally, it's going to be a minus. It's going to be x cubed y over z squared, cosine y over z dz. So that should be it. So this whole function here is what df ends up coming out to be. This differential one form. Okay. Let's go back here. This is just a thinking exercise. It's not really a proper exercise to calculate something. It's just, you take a zero form and you take the exterior derivative of it and it takes you up to a one form. But what is that really doing? Like, what are you, like, there should be some kind of geometric interpretation. And it's just, you're leveraging the fact that the coordinate directions, when you map them through F at a point, when you map a neighborhood through F, it kind of like sends your coordinate curves from one place to another. And you can imagine that you look at the tangent spaces and some pre-picked out coordinate systems, both on your domain and your codomain manifold locally. And you think about where the coordinate directions get sent to in the new coordinate system. And that gives you a linear map locally. And so that's what the exterior derivative of the zero forms is doing. It's a one form that's acting like a, that's acting in some sense like a matrix to send the coordinate directions to somewhere new in the new coordinates. Okay, so it's just like draw a picture of that, I guess. But that interpretation kind of fails when you go from one forms to two forms, and so on. There's some books on general relativity that try to extend it further, and I had an example at the bottom somewhere, but it's difficult to piece together what exactly the geometric interpretation should be. We did this one in class, but just in case, I'll redo it real quick. Yeah, so you take the derivative, or the one form for integration of areas in 2D in Cartesian coordinates. So that's dx wedge dy. And you want to show that this is equal to r dr wedge d theta. Right, so that's a this is called an area form on R2. And the reason it's called an area form is because anywhere I look at it, I can evaluate a two form on any tangent space. Right, and so the tangent spaces to R2 look like R2 themselves. Let's say this is TP R2 at a particular point P. And no matter what vector I plug in, as long as it's not equal to 0 itself right here, then I'm going to get something not equal to 0 when I plug that in. Right, so this direction is del x, this is del y. If I plug in a vector, a tangent vector to this point P into here, as long as it's not 0, I'm not going to get 0 as a result. Okay. So this is called an area form. There are other area forms. You can like scale it. You can do like 3 del x or dx wedge dy. You can do -5 dx wedge dy. But yeah, these are the area forms. You also have volume forms in R3, and they look like dx wedge dy wedge dz. And I should say that any manifold that's orientable, you can actually characterize it in terms of having a full rank hypervolume form. So if I have like a 3-manifold, I just need a volume form. If I have a 2-manifold, in order to show that it's orientable, I need a globally defined area form. Right? So something that looks like this cannot be constructed on a Mobius strip, for example. Not globally. And locally it can in a particular coordinate system, but not globally. So how do I actually show this? Well, firstly we know x is equal to r cosine theta, y is equal to r sine theta. Let's switch colors. Green's fine. And so we can rewrite this now. Dx wedge dy equals dr cosine theta wedge dr sine theta. This is equal to, differentiate with respect to r, it's cosine theta, dr. Differentiate with respect to theta, that's minus r sine theta, d theta. Now wedge that. Same deal here, sine theta dr plus r cosine theta d theta. This is equal to, well, the wedge product is associative, distributive, so on, anti-commutative. So we can now multiply doing FOIL if you want. I mean, you can do it in a more natural way, but just FOILing's fine. These two are going to disagree, so let's write them. I'll do them in red if they're going to die. Cosine theta, sine theta, dr, wedge dr. You need to preserve the orientation. This one's going to live. It's going to be plus r cosine squared theta, dr wedge d theta. The middle is going to be minus r sine squared theta, d theta wedge dr. And finally, minus r squared sine theta cosine theta, d theta wedge d theta. Okay, so now these die. And you're left with this. You can factor the r out. Cosine squared theta, dr wedge d theta, minus sine squared theta, d theta wedge dr. Anti-commute these. Factor that out, and you get r cosine squared plus sine squared theta, dr wedge d theta equals r, this is 1, dr wedge d theta, and you're done. Okay. So that's how you do change of coordinates. Anytime you want to do change of coordinates in calculus, you can just leverage differential forms, and you don't have to remember rules about Jacobians. It's just direct and natural. Okay. Every kind of integration you might think of doing from Calc 3 or anything Calc 2 is naturally expressed here. It just works out like you would expect it to. On to probably pullbacks and integration. All right, did I skip any? I think so, right? 9. I may skip this one.
Is this one too long?
I don't remember the proof off the top of my head. It's probably really simple, but I remember. It should be in Schifrin too.
Oh.
Yeah. It is the case. I mean, you can always commute pullbacks with the exterior derivative. So like what that means is, what are you doing here? You're taking omega, which is, let me see what it's on. It's an exterior, it's a differential form on, what is it defined on? It's defined on an n-manifold, and it's a k-form. So it's a k-form on some n-manifold, where k is less than or equal to n. So, and you want to pull it back. So g is a parameterization of a function. So I should say u, which is a subset of rk. This is a function which maps you to m. Remember, this is an n-manifold. You have to satisfy this being, satisfying the full rank condition, which is the determinant of dg has to be greater than 0 at all but like a measure 0 subset of u, but that's fine. It just means you can't like have a parameterization of a manifold that kind of folds over on itself in a creased way. So it can't be like singular in some fashion. It can't have like jagged edges and stuff. It's just gotta be nice and smooth. And so yeah, GU is like the submanifold that you're thinking about integrating omega on. And what you'd like to do is you'd like to say, okay, well, I've got this thing that does this. Got a diagram. So U lives in, so this lives by inclusion in RK. That's just an open set. You have this mapping over by the parameterization to M, which is the manifold where G of U is a submanifold of. You also have a differential form, which maps you down to R. This is called omega. I should be more careful. That should map you from tangent. Yeah, so you want the tangent bundle. So this is the bundle map. You have the differential form coming out of here and mapping you to R. You also have TU, tangent bundle over U. You have the exterior derivative of G. And namely, you want to get a differential form on U. So this is now going to be G star of omega. So this is the induced map by the pullback. Exterior derivative of this thing, which is a map from TU to R. Right, think of what this is first. G star omega is in, it's a differential form on U, and it's a K form. So namely, this should be a differential form of grade K plus 1 on U. And it should equal G star d omega. Is that right? It's not quite true. It should evaluate to the same thing on the tangent space. I'm being stupid. This is only for one forms. So I would need to like take this and do a product of it a certain number of times, namely K times. Oh. And it gets messy if you try to fix all this. But anyway, just symbolically, you can commute the exterior derivative with pullbacks, and it's fine. Right, because taking the pullback of a differential form, G isn't like particularly opinionated about what it's pulling back. Like G star, you can put any differential form after it. It doesn't have to have a particular grading. Like it can be a K form for any K. So that's kind of why this equation makes sense in general. You don't have to worry about the degree or the grade of omega. It's kind of unimportant. This little equation nicely just always works. I forget where you see it used, but I mean, I've had to use it in a couple of exercises I did before, but it is helpful. Let's see. Is that exercise 10? Do I have a 10? I do. It's right here in the middle. Okay. So what is this saying? Going from this line to the next one, I have the circle. And so what are we doing here? We're taking the circle and we're writing it in two parts, namely the upper hemisphere or semicircle, which is S1 plus, and then we have S1 minus on the bottom. So if I just draw what is going on in that example, you've got the unit circle in R2. Okay, this top part, including the part on the real or on the x-axis, is called S1 plus, and the bottom part, this is S1 minus. And normally you have an orientation plucked out, chosen by the standard area form, namely dx wedge dy. Okay? So the orientation that agrees with this is the counterclockwise one by the right-hand rule. Right. So the idea is you want to think this direction, that's dx in some sense. Dy is in this direction, and by the right-hand rule, if you think about this living in R3 or something, like if you look at this plane in R3, you have these three directions. You go dx, here's your unit circle, I guess. Here's dy, and then by the right-hand rule, your dz is going to be pointing up. Okay, and you want to curl around in this direction counterclockwise to satisfy right-hand rule. So this is just kind of convention, but this induces an orientation on S1 plus and S1 minus, which is in agreement with it counterclockwise. right? Because they're both parts of the red. I drew them in a different place, but really you should think of them as living here. So S1 minus should namely go to the right, and S1 plus should go to the left. And why is that important? Well, it's because when you integrate a derivative, or excuse me, a differential form over a manifold, namely I've pulled back alpha from being integrated on S1 plus to on the parameterization of S1 plus, which is -1 to 1 on the real number line. Because S1 plus lives in R2, but the parameterization lives in R. So where'd I go? Yeah, so at time, so think of the real number line. Here's -1, here's 1. At time -1, I start right over here on S1 plus. I should get rid of these. Okay, what just happened? There we go. I start here, and then as time goes on, I'll progress throughout S1 plus until I finally end up over the other side. Okay, so you can imagine I walk along this, that's the same as walking along this. And you can actually tell this because of how I wrote that S1 plus is being parameterized. And I actually gave an explicit formula for G, right? G plus is just this thing, U, and then in the second component you have square root of 1 minus U squared. So you can actually compute these things. And the domain of G plus is -1 to 1. So I pull back alpha by this thing, and it stops being a differential form on R2, and instead becomes a differential form on -1 to 1. And so I integrate it over that domain. That domain has a natural orientation inherited from being a subspace of R with the usual length form, which is dx, and it's left to right. And so in order to make this agree with the direction that I want to have, you have to be careful because G is not this. This is negative G. Because think of what G is doing. It's going from left to right in R2 because it says start when -1 is what U is. Start on the left side at the X component in R2 is -1, and then go to the right. So it goes around the semicircle from the left side around the top to the right side. So you can actually look at the parameterization and see what exactly it's doing, and you need to cancel that out to make it go backwards. And to do that, you put a negative sign. Okay. Because if I were to flip the orientation of the integration, it would be going from -1 to 1, and that's like putting a negative sign. It does the same thing, as we know from calculus 2. So that's why minus appears there. It's because you want to have the same integral. So in order to get that, you need to have backwards from the orientation that G plus specifies that you're going to have when you do the integration. But the other one's fine because you're already going from left to right, as this says, at this U up here. Along the bottom, you'll go left to right. So it works. Okay. When you're using Stokes' theorem and you're breaking integrals up into parts like that, you in general have to be careful about your orientations because they do actually matter. And the mechanics are a little bit different from how you're probably used to if you aren't normally doing differential forms. Because your domains have orientations on them naturally. So you have to think about it. It's not written in the integral. Let's see. Okay, 11. In polar coordinates, x equals r cosine theta, y equals r sine theta for R2. You may write S1 as being radius of 1 and let your angle go through all the angles possible. So that's S1. And we're building a differential one form, alpha, which is, what is that? -y dy plus 2x dx. So that's actually what we were integrating up here. It's the same alpha. See, this thing. So -y dx plus 2x dy. So we want to integrate that on S1, and it should be easier, hopefully, using polar coordinates. And we want to choose a different parameterization for G this time. We should not probably have to break it into two parts, I would imagine. Like we did up here when we broke into semicircles. And yeah, it should be all right. It should be easy to do. So let's write out what we have. S1 is equal to 1 theta for all theta. Alpha is equal to -y dx plus x dy. But this is, of course, by the polar coordinate transformation. R sine theta dx sine, r cosine theta plus r cosine theta d r sine theta. And we should be able to actually simplify this into basis forms. So this gives me -r sine theta. And then you get cosine theta dr minus r sine theta d theta plus r cosine theta sine theta dr plus r cosine theta d theta. And I'm forgetting something. I forgot to put a 2 here. So let's re-include that. And then you have minus r sine theta cosine theta dr plus r squared sine squared theta d theta plus 2r cosine theta sine theta dr plus 2r squared cosine squared theta d theta. You can simplify it yet further. So grouping together, you get r sine theta cosine theta. So I'm factoring that out of both of these. And then you have minus 1 and you have positive 2, so you just have one of those, dr. And then you have one of these r squared sine thetas, and then two of these r squared cosine thetas. So you get plus r squared. And then you have 1 plus a cosine squared theta d theta. Okay. So that's what alpha is for us. Now, namely, when I integrate this around, so firstly we have to figure out what g is, right? So g eats theta, and it's a map from 0 to 2 pi. So this is the parameterization of the circle. And the circle is one-dimensional, so it needs to have a parameterization being a subset of R, and it's going to map to R2, and it's given by this. G theta equals 1 theta. Okay. Now what I want to do is I want to integrate. So firstly I want to take S1 and integrate alpha on it, but this should be equal to integrating on the parameterization space 0 to 2 pi. I should be able to integrate the pullback of alpha by G. All right, so think if G is a map from 0 to 2 pi to R2, and I have something which is a differential form on R2. So alpha is a differential form on R2. Then G star alpha, I'm pulling it back to the parameterization space, so it should become a differential one form on that space. Okay, that's there. So we want to integrate that on here naturally. I don't really have to write down where I'm even integrating them. It's just natural. If I didn't write it, it would be obvious from what it's a differential form on. But the way you actually do this is you say, okay, well, now we need to compute what G star alpha is. Okay, so in other words, I can say G theta as a function is equal to, well, it lives in R2, the value does, 1 in theta. If I want to pull back G star alpha, well, remember what alpha is a matrix. It's a differential one form, so I should be able to write it in terms of R and theta components for R2. And I get R sine cosine. And I should do it as a covector, right, because it's a differential form. And then the second component is R squared, 1 plus cosine squared theta. Okay. Well, what is G star alpha then going to be? You take G, let's see. It's going to be a map from, it's going to be a differential one form. How did we compute these again? Let me look at an example. Where'd they go? So here they've got u being in there, and they stub that into negative y dx. Is that right? Yes, it is. All right, so they take the differential form. Now, this is the rth component, and this is the theta component for us. And I'm just saying, like in R2, we've got a coordinate system, and the components are r and theta. This being the same theta, that isn't the same thing. That's just a coordinate for this space. I could have written x here and then x here, and then I still would have said this is r and theta components. Okay. So what you do is you take r and theta components and you stub them into the differential form. Okay. So that's going to be yeah, that's going to be 1 is r, and then sine theta cosine theta. And then you have 1 again for r here, and so you have 1 plus cosine squared theta. Okay. Now I'm trying to think of why this doesn't come out to be a one form on a one-dimensional space. So this is, we know this to be sine theta cosine theta dr plus 1 plus cosine squared theta. The matrix notation for this is a little bit confusing. Note, r, when we do the pullback, is 1. So this just becomes 1. Okay. So really I should be doing the pullback. Okay. For these differential forms. So this makes it more natural. And then we can commute d with the pullback. So this ends up being d of g star r plus 1 plus cosine squared theta d g star of theta. And remember that g star of r is just 1. And then g star of theta is just theta. So d1 plus 1 plus cosine squared theta d theta. d1 is the exterior derivative of 1, which is 0. So you end up getting 1 plus cosine squared theta d theta. And this is what you want to integrate, right? So this ends up being 0 to 2 pi. And the orientation here is already good. We're already going counterclockwise by virtue of my definition of g up here, wherever I put it, this thing. And g star alpha is just 1 plus cosine squared theta d theta. Okay, and then you can evaluate this in the usual way, just integrating, plugging things in. If you want to, you can rewrite this way. So this integral is easier to do in polar coordinates, and you would expect so because you're holding the radius constant. But if I wanted to compute this thing and I had just alpha, and I wanted to do the pullback of alpha by g, I could write g star and then write what alpha is, and well, I know it's sine theta cosine theta. I wanted to do this quickly, dr, and then I had what, plus 1 plus cosine squared theta d theta. And so you just say, okay, take g, replace the r and theta components with whatever they are in g, so 1 and theta, and this just becomes this, sine theta cosine theta d1 plus 1 plus cosine squared theta d theta, replacing theta with theta, of course. This all goes away and you're left with just this. So it's really not a bad computation. I just took forever to do it. Okay, so pullbacks are nice. That does it for that exercise. Pretty lengthy one, but it does kind of show the power of being able to compute these pullbacks because it gives you a general way to integrate things on submanifolds. It's nice. And sometimes it's like kind of an implicit procedure, so you can reason about what the integrals should be without actually having to compute them by hand sometimes. And then finally, just to lubricate things a little bit, there's some exercises about actually computing these pullbacks. So let's do that. Let me pull up my snipping tool. Okay. Back omega by g. Okay. So what is omega? Omega, these are both one-dimensional, right? So it should be natural. I should just replace, I mean, you can think of g, u, as being matrix valued with sine u. And this is the x component of gu. So omega pulled back by g should just be d sine u. 1 minus sine squared u. But then you have to evaluate this thing, so you end up getting cosine u over 1 minus sine squared u du. And then the bottom just simplifies and you get du. Okay. Because the bottom is cosine of u. Okay, so that one's easy. Namely, this is now a differential form on not r, but it's a differential form instead on negative pi over 2 to pi over 2. Okay, because we pull it back from being something on R to being something on the domain of the parameterization of the submanifold. Okay. Basically get to be nice. It's just that sometimes you forget if you don't compute them for a while. Yeah, so omega's a one form. We're going to pull it back by G. Think of what these components are. This is X. This is Y. So namely, you have negative 3 sine 2v d 3 cosine 2v plus 3 cosine 2v d 3 sine 2v. So you can factor out 9 from both sides. Okay, and then you can compute those derivatives. And you should get a 2 to come out. And I'll just write it. 2, and then you have positive, because you get a negative from the cosine differentiated. Sine squared 2v dv plus, just checking to see if the dimension of the domain agrees. It does. So that's cosine squared 2v dv. And namely, this becomes 18 dv. Okay. And this is in the differential one forms on R instead of being on R2 now. Right, because we're pulling back onto R from R2. All right, let's see the third one. To R2. So this is the X component, this is Y. You just stub them in here. So G star omega equals negative 3u sine 2v d 3u cosine 2v plus 3u cosine 2v d 3u sine 2v. Now notice the difference here is that we have these u parts. We didn't have that before. Sine 2v. Is that right? Yep. Okay. So now, and of course we can factor out 9. Negative u sine 2v d u cosine 2v plus u. And moreover, I can actually factor out a u. 9u. Come on. Cosine 2v d u sine 2v. And if you're wondering, no, you can't factor that in here. You got to actually differentiate with respect to it. So that's 9u. Negative. Now you differentiate here, but we'll leave the other stuff constant. So this is going to be cosine 2v du. U, well, 2u sine 2v dv. Right. Hopefully I did that right. Plus, and then you get cosine 2v. And then you have the result of that exterior derivative, which should give you sine 2v du plus 2u cosine 2v dv. No. This is going to be 9u. Should we combine things? Probably should. So 9u. I'm going to do the du part now. So that's going to be, we'll think this cosine 2v, this cosine 2v are both positive. Then you have a negative sine 2v and a positive sine 2v. So those are going to die. Okay, so those get killed with each other mutually. What about the others? Those seem like they'll live. So I'm going to have this with this, and this with this, and I should get positive 2u sine squared 2v dv. And the other one has a dv as well, so I'll just leave it out. plus 2u cosine squared 2v d all dv. So that ends up being 18u squared dv, and that's it. So that's now a one form on R2. I know it only has one thing here, but you get another coordinate as well, and also even if you didn't end up with another coordinate, you still pulled back on R2, so it's still a differential form on R2 even if it doesn't have other coordinates. So yeah, we end up with a one form on R2. Now pulling back from R3 to R2, again a differential one form. Okay, so now this is our x component, this is y, and this is our z component for g parameterization. And we want to do g star omega equals, well, z is v dx cosine u plus x, so cosine u, dy, which is d sine u, plus y, which is sine u, dz, which is v. Now evaluate v negative v sine u du plus cosine squared u du plus sine u dv. Very easy, just combine cosine squared u, so I'm just combining these two du terms, minus v sine u all du plus sine u dv. Done. And this is a differential one form on R2 now, the domain of the parameterization G. Okay. Pull back from R3 to R2, but instead of a one form, now we're pulling back a two form. It should work the same way, but just to see the calculation, I'll go ahead and do it. So, right, what are the components? This is again x, this is again y, and this is again z. And g star omega, remember it doesn't matter what grade omega is, like it's a two form here, it doesn't matter, I can still write g star. Found it. I'm going to pull it back. But we have to have, yeah, it doesn't matter what grade omega is, this just works. So this becomes z, so really I should write g star, if I'm being formal, I want to write of z dx wedge dy plus y dz wedge dx. You don't have to do this, I mean you can just eyeball it. And this distributes, so you end up getting g star z. It distributes over wedge products, it distributes over exterior derivatives, so you get d g star x wedge d g star y plus g star y d g star z wedge d g star x. Okay, but that's all a mess, so we don't really do that in practice. You just write in what z is. So g star of z is just v dx, which is cosine u, wedge dy, which is sine u, plus, and then you have y, right, up here. So that ends up being sine u, dz, which is v, wedge dx, which is cosine u. Now simplify. You end up getting v negative sine u du, oops, wedge cosine u. So I should be drawing parentheses around these, du, plus sine u. dv is already simplified, so you don't have to do anything. And then put sine negative sine u du. Okay, so simplifying further, I just apply the wedges. I can pull out the smooth part, negative sine u and cosine u. So I get negative v sine u cosine u. And then I have du wedge du. I meant to notice this earlier, which of course is 0. This whole thing is bogus. But the other part, we have plus sine u. You can factor out the minus sine u and write negative sine squared u dv wedge du. But because we have uv as the chosen orientation for the coordinates for R2, namely the domain of G, we want to anti-commute to get positive sine squared u du wedge dv. And of course, this is a differential 2 form on R2, the domain of G. So we pulled back a differential 2 form from R3 to R2, and this would allow us to integrate on a surface in R3. Okay. This is, however, not an area form because sine squared u can be equal to 0 somewhere. But that's not too important right now. This is a little bit tough, so we need to be careful. We can't write x, y, z anymore. So this is going to be x1, x2, x3, and x4. Our coordinates for R4. Now, g star of omega, we're going to pull this back to a 2 form. Our x2, which is sine v, dx1, which is cosine u, plus x3, which is sine u, dx4, which is cosine v. This should be pretty easy, actually. So this gives negative sine v, sine u, du. Then you finally have minus sine u, sine v, dv. So what I can do if I want is to write negative sine u, sine v, du plus dv if I like, but that's as simple as I can get. This is not quite right. What's going on here? Oh, I see. So we're pulling, yeah, we didn't get a 2 form. We get a 1 form on R2 because we started with a 1 form. So that's it. So this is in the 1 forms over R2. All right, cool. And to keep it as simple as possible, this is the simplified version in terms of the basis, linear combination of the basis covectors. Now 7. So we've got a 1 form again. Is this the one we just did? X2? No, it's not. So we should get a little bit of a different answer. Again, same coordinate choices. Cosine u is x1, cosine v is x4, so on. G star of omega should be a 1 form on R2. So we're pulling back from R4, and it already is a 1 form. And it should be cosine u dx3, so that's d sine u, minus x2, which is sine v, dx4, which is cosine v. All right, this gives us cosine squared u du plus sine squared v dv. You can't simplify this any further, so we're done. And this, again, is a 1 form on R2. Last one. Form on R4, and we're pulling it back to R2, which kind of makes sense. You would probably like to integrate that on R2. G star omega is, again, this is x3, x4, x2, x1. So you get negative sine u d cosine u plus cosine u d sine u wedge negative sine v d cosine v plus cosine v d sine v. Okay. Now this is sine squared u du plus cosine squared u du. Wedge sine squared v dv plus cosine squared v dv. Namely, we can factor out the du on the left side, and you end up getting 1 just du wedge dv, and you're done. And this is a 2 form on R2. Okay, so that's it for the pullbacks. So hopefully it should be pretty clear now, like
Yeah, it
how
is.
you actually can.
I
know
can
it-
we also
it's-
do
it's-
a can we also do an application based problem of whatever we have studied so far? Like
Yeah.
and
I don't have Schifrin on hand. Let me see if I have a different book. I might be able to pull some examples. What's their 188? Here's some. More. Nice exercise about winding numbers in R2, the origin taken out, but I don't want to do that. I want to do a computation. Let's see.
Or any physics problem that uses this?
I don't have any physics textbooks on my desk. You can do this anytime you do any integration. In particular, I think if you want to integrate something on a sphere, like if you have a function on a sphere and you want to integrate that, you can use this idea. So let's see. Let me just throw out an example. We can do something simple.
Okay.
So let's say I've got in R3, I've got a function that goes to R. Let me just think if that's what I want to do. Yeah, so I want to build a function, and I don't want to do this.
I have a problem. If
Okay. I was going to integrate this on the sphere, but what's your suggestion?
Do you know electric field? I mean, of course you would, I guess.
Maybe.
So imagine a sphere of radius 1 having
Okay.
charge q1,
Okay.
and that is placed at a distance d with another sphere of radius r2 and charge q2.
Okay.
And we want to find dot product of their electric field. We're going to integrate this in the entire volume R3.
Okay, so you need like Coulomb's law.
Yeah.
Can you recall the law? I don't remember. It's been so long.
Yeah, it for a point charge it is kq upon r squared
You said this?
upon I mean kq over r squared.
Oh, okay. Gotcha. And K here is the
Coulomb's constant, or
okay. Okay. This is the field potential.
by a point charge.
Okay.
This is the value of the electric field by a point charge.
Gotcha. Okay.
But the charge is distributed on the sphere.
So this is the potential function, yeah?
Yeah.
Okay.
I mean, potential function will be derivative of this function.
Gotcha. No, other way around. So the potential gives you the gradient flow. So the gradient of this will be the field that is the forces. In general, for any potential. So if you this is, I guess U equals this thing. You take nabla U. This gives you the field due to whatever potential you have in general. So the same for gravitational potential. Right, because think you have in a uniform gravitational field, you have a linear potential function. So the forces.
And the gradient of that function gives you the field or the force.
Right.
Yeah.
Let's see. And this is just the magnitude of the charge, yeah?
Yeah.
Okay. All right, so you're wanting to know, let me draw the picture. You've got a unit sphere in R3. This is a unit sphere. And you're doing what with this?
There are two spheres, one having radius r1 and charge q1 on its surface, and the other having radius r2 and charge q2 on its surface.
And
they are separated by a distance d. Their centers are separated by a distance d.
Okay. This is R2, and each one has a charge. Q1, Q2. Now, I'm a little confused about one thing, which is, but what are you? Firstly, here's right. So, what are you trying to integrate?
I'm trying to integrate their dot products, E1 dot E2, or as you've written U. I mean, this is a vector, right? The field is a vector.
F is, yeah.
Field is also like electric field is also considered a vector.
That's right. So F is going to be, but U is just a potential function, so it's part of the like energy.
Oh, if so, the potential function does not have square in its denominator.
Okay, that makes sense. So it's going to be R. Gotcha.
And
Oh, I see
and
now.
we wanna. Oh yeah,
And so what do you?
I'm trying to find E1 dot. I mean F1 dot F2. This integral in the entire volume. Like I want to find the volumetric integral of this quantity, the dot products.
I don't know what you mean exactly. Like there's a specific geometric object I'm trying to integrate, and it's not clear from that. Because what I have is I don't know how R1 is supposed to relate to anything here, because the charge is something that is inherent to the particle, and the position is known by the particle. I don't know what R1 is talking about, but I assume that you had meant like integrate the electric field over R1, and then integrate it over R2 or something like separately. But
So they let's take a general point in the space x, y, z. At that point, there is some contribution of the first sphere, some electric field contribution by the first sphere, and some contribution by the second sphere. So
yes.
I want to take the dot product of those two contributions, and then this is a quantity. I want to multiply by the differential volume at that point, and I want to integrate this in the entire volume.
So is the field coming from this point at the center of the spheres, or is it coming from every point on the surface?
Every point on the surface.
Oh, okay.
Or we can also do it for a simpler version if you want.
A point mass or a point charge.
Yeah.
If you do it, let's see. So we want to integrate over the whole thing. The field contribution that it has. So what you might do, it would be simple enough just to do it for a single sphere. Like it would be essentially the whole problem anyway.
Oh yeah.
So what you're doing here is you're integrating over the sphere a function which is constructed by looking at the point that you're at. You plug it into the function, and the function tells you the distance to p.
Mm-hmm.
Okay. So what we're doing is we want to find the average distance to p in some sense, and then divide by the surface area of the sphere or something. Or I mean, you don't have to do the surface area. You can just do the volume, whatever you like. So yeah, let's look at an example first, and then we can just say, okay, plug in the difference, because R for us is going to be this thing. It's just the distance between p and the function, the point that you're looking at. So it's like p1 minus x1 squared plus p2 minus x2 squared plus p3 minus x. That thing. But you're already there if you have the following, because once you get that much set up, it's clear how you integrate. You just do the usual like Calc 2 integration. But if you want to integrate a general function over a sphere, one that seems kind of natural to try to integrate is f takes you from points in R3, maps you to R, and it's defined like this: f x y z equals z. I'm going to switch to writing like American z's for a second, because it's going to be hard to read. Okay, so it just is the height function basically. I want to integrate that. You would expect this to spit out the average, like times something, right? So if you are centered at 0, you would expect this to spit out 0. But to actually compute this thing, let's see. So let's say S2 is equal to the following. You can use a variety of things. You can use coordinates for R3, you can use cylindrical coordinates, or you can use Cartesian coordinates. We'll do that. X, y, z, such that x squared plus y squared plus z squared equals 1, or just r squared if you want. But this isn't enough. We need an actual parameterization to do a pullback of, right? Because I want to integrate this thing in some sense on pullback. So when I really want to integrate, I can't just integrate a function anymore. I'm not able to do that in calculus. I have to integrate a differential form. In fact, the differential 2 form if I want to integrate this on the surface of the sphere. So that 2 form might make sense to, how should we do that? We want f, you kind of have to think about what exactly you want. You want an area form on a sphere. So what is this omega going to be on R3 that will pull back to something nice on R2? Let's see, let me think about that. I'm thinking you can just take the 3 form, maybe. Does that work?
Yeah.
So I was thinking you
it'll
can what if you take the volume form on R3 and try to pull back that to R2, what happens? So let's see what happens. Let's take a simpler submanifold to integrate on. Like let's say, G is UV and it maps you over to this thing, 0, or sorry, UV and then 0, so it's 0 height. Well then imagine what this is going to have been. Well, that's just going to be this. Oops. du wedge dv wedge d0. Well, that's just 0.
Yeah.
So you can't really pull back in that way. If you want to integrate over the surface using a 3 form, it does not make much sense to do that. You want an area form on the surface. Let's see.
Can we
how much-
parameterize sphere? I don't know, how would you parameterize that?
So to parameterize a sphere is not too bad. You can take, you need u and v, and then you might say, okay, just take. You could do it in 2 parts. In fact, you can do uv, and then you can do like u squared plus v squared square root, and that would be the plus part. And then you can do a minus part, and then you can integrate over 2 separately.
Oh yeah.
Or you can use the following. Namely, think about a spherical coordinate system.
That'll be easier, yeah.
Probably harder to think of, but the end integral is going to be 1 integral instead of 2. So what you would do here is think, okay, how do I construct the parameterization for sphere in R3 with 2 angles? Well, R is going to be 1. And then I've got an angle, which is the longitudinal angle. This is theta. This is x and y. So, of course, this is going to have some part of like cosine in it.
Yeah.
This is going to have some part of sine in it. Then, if you think about phi is the meridional angle. This. And all you need to know to figure out z is phi. And in fact, that is sine of phi. Then you just need to multiply with something else here, and it turns out that's cosine phi on both parts. But quite easy to figure that out, actually.
Oh yeah.
And if you check, take this, square it, take this, square it, take this, square it, you're going to get 1 if you add all this together. So it works. I mean, that's not proof that it works, but it's like, pretty good verification that you did the right thing.
Yes.
Right? Because if you square that stuff, you're going to get c squared plus s squared, c squared, and then s squared. Then, namely, this is going to be c squared plus s squared, where you have c squared plus s squared. So this gives you 1, and then the rest of it is just 1.
Yeah.
So it's quite nice. And then, the pullback onto here is the same issue. If you pull back this thing by this parameterization, you'll still get 0, probably. Yeah, you are going to.
We should, yeah.
So then it seems like pullbacks are not the right way to take a 3 form and get down to 2 forms. Because they're going to preserve what kind of form you are, what grade your form is. What you might do, let's see, how would you do this? You want to have some differential form built off of f that you can integrate on the sphere or surface. F is our function that we want to integrate, namely the height function. We want to integrate that on the sphere and get something. Firstly, what does it even mean to integrate this on R3, right? Well, you want to integrate f, x, y, z classically, right? Before Cartan, you would do a triple integral, and you would say integrate this on R3, dx, dy, dz. When Cartan came along, this looks like this now. Take the volume form, the oriented volume form, and just multiply it times the function that you're trying to integrate. And you've got a definition of volume. And, this works. This is what you would expect. And it gives you the same thing as before, of course. What we need to do is we need a way to have an area form instead so that we can integrate this f function on the surface. We need the area form to agree with the standard volume form on R3. So we need a way of projecting metrics down from R3 to R2 to do this. Let's see. So you might think of finding a basis for R2 at every point. So namely, think of, I mean, it's clear if I wanted to integrate this on the flat plane that has no z component, it's just z equals 0, I'd probably want to do this. This would be the area form that would agree with the volume form in some sense. Right, that kind of makes sense. But what's going on there is I'm taking dx and dy and wedging them, which is a right-handed basis for the sphere cotangent space at every point. Well, not the sphere, but the plane. So you can think of the plane as living in R3, like this, and you pluck out a basis for it. Namely, x and y. And then you just take their sharps, or their flats, sorry. So you form a right-handed basis, you get this parallelogram that's circling counterclockwise, and you sharp this, and you get dx wedge dy. So yeah, how do you do this in general? Well, think about the sphere. We've got that parameterization that's nice. Right, the one that you showed me, or that we were building with u and v. And it looks like this. Yeah, that's, what was it? Cosine theta. Let's use u. Cosine v, sine u, cosine v,
Sine
and then sine v. Now, I don't know if you remember when I was showing you this before, but it wasn't with everybody. But you can build the first fundamental form for a surface. And what that looks like is you look at your tangent directions. So imagine the sphere. And imagine, I drew that really badly, but you know what I'm trying to get at.
Yeah.
And then imagine you take a point P, and you want to figure out what happens if I move by increasing u. Well, I'm going to go that way. Or, sorry, I'm going to not go that way. I'll go the longitudinal way. If I increase v,
you
I
said
increase.
u?
Yep. This is
Oh, yeah.
del u. This is del v,
Hmm.
so to speak. Now, importantly, this is absolutely not what's happening. What's actually happening here is that del u is tangent. Think of g. uv, or coordinate system for R2, the space that's parameterizing. But, yeah, so del u lives in the tangent space to R2, tangent bundle to R2 at the point. And what I'm doing is I'm saying, okay, take dg, which is a map now from the tangent space. Think of g as being a map from R2, R3, right? It takes you from the plane to the volumes, but it only maps the plane specifically to the sphere. So it takes you from the tangent space, dg takes you from the tangent space of R2 to the tangent space of R3. And this thing now is dg of del u. And this is dg of del v.
I see.
Hopefully that makes sense. So now you actually get a basis for your tangent space at this point. So where was I going with this? So we're trying to integrate things, and we want a volume form. Now, you need to make sure that your, let's see. You should be able to use the metric on R3, which is a 2 tensor, a 1, 1 tensor, and it eats 2 tangent vectors, and it spits out a number, and it acts like inner product, right? So in R3, I can take a point, and I can take 2 vectors, and I can do a dot product. That's our normal metric. And you can figure out if things are orthonormal or not. Right? You can figure out if they're orthogonal, you take their inner product, check if it's 0, and then to check if it's normal, you dot product it with itself. So I can actually take these bases that dg is giving me, and even if this spits out some things that, dg of del u and dg of del v are not an orthonormal basis for a tangent space, as long as neither of them is 0, which happens everywhere except that it happens everywhere actually, because we're using nice polar coordinates. As long as they're not 0, I can Gram-Schmidt them and get an orthonormal basis that I can do integration on, and it will act like an area form that agrees with the metric in R3. So let's see. I think these are just nice. I think they're fun. So let's actually look at dg of, so what's dg? That's going to be negative sine u cosine v du minus cosine u
Sine v.
sine v dv, yes. Yeah, so cosine u cosine v du minus sine u sine v dv, and finally cosine v dv. So now I can take this as being like a matrix, actually. It literally is. It's a Jacobian. So this is going to now be negative sine u cosine v, negative cosine u sine v, and cosine u cosine v, negative sine u sine v, and 0 and cosine v. And this eats things in R2 and spits out things in R3, so it works exactly like we would expect. Namely, I would like to check the following. I'd like to check dg of del u, which is just this Jacobian, times 1, 0. So we end up just getting this. So that ends up being negative sine u, cosine v, cosine u, cosine v, 0. And also dg of del v is the right column of the Jacobian, so that ends up being cosine, negative cosine u, sine v, negative sine u, sine v, and cosine v. Namely, if dg as a matrix is orthonormal, you're good. But, right, the columns are orthonormal. And it's actually quite easy to see, but you just, you check these things. So you take the inner product imbued by the inner product on R3. You actually have to say that you have the normal metric on R3. So this is the typical one. This just ends up being the dot product. So it's sine u. So let me just write SU. Two negatives cancel. Cosine u. So I'll do this. SU cosine u. SV cosine v. And then you have minus SU CU SV CV. So these two die together. And then finally plus 0. So yeah, they're orthogonal. And then secondly, you can check that they are normal, I think, right?
Yeah.
So dg del u with itself should give you 1. This with itself is going to give you sine squared, cosine squared, plus cosine squared u cosine v squared. Well, no, that's just going to give you cosine v squared. So you have to be a little bit careful here. Yeah, that makes sense. And then, namely, dg del v in R3 multiplied with itself, the length of it squared. So what I'm saying is the length is the square root of this quadratic form. So this should be CV. That's cosine v. And this one is going to have been sine squared v plus cosine squared v. That one actually is 1. Okay. The length of this vector is cosine v, so we want to normalize it. And the basis, the orthonormal basis for R2, or for the sphere's tangent space, is this. That thing. And dg del v. Okay. And when I say that it's an orthonormal basis for the tangent space, I literally mean if you look at the sphere and you pick out a point, you literally get two orthonormal vectors right angled each other that span the tangent space and have, length 1 each. So it's quite nice. And you would want to take the following integral. So S2, and you take f you'd pull back f to, so it's g star of f. And I might even just choose a different basis for u to make this nice. But I don't think it matters. Yeah, you can just do this.
I think it is already
This will
nice.
be a function. Yeah, should be. And then you put over cosine u.
U.
And then you have dg del u wedge dg del v. And you can just take what these are and simplify them. And you'll get this nice, nice little thing. I should be careful to say what am I doing here? So I should get a column vector. I mean a row vector, so this should be transposed. Of course. Is that right? No, it's not right. It's supposed to be in the tangent space, so that's wrong. Oh, these are a basis, so I want to, right, these are tangent vectors, so I want to get cotangent vectors, so I shrunk them. And it might be that you want to do this, actually. We're going to integrate with respect to those coordinates locally. I think I'm being stupid here. No, I've done the pullback, so I don't want to do that at all.
Yeah.
I've done, yeah, my coordinates have changed altogether. So it's now going to be du wedge dv. Am I being stupid? Am I being stupid? What am I doing? Seems like this fixes it. And then you just integrate on, should go, both of them should go 0 to 2 pi.
Yes.
So if you want to make this be classical, it should be like this. And then it's easy to pull this back.
Yeah, I can do that.
Because f is just a function like the height, and you have, in our case, that z is that. Yeah, g star of f is just sine b. This ends up being tangent of, what was it? Was it u? Oh, it's v, so you can't do that. Sine b over cosine u. du dv. 0 to 2 pi in both cases. And then you're done.
How do you calculate the pullback so fast again?
Oh, yeah. So I'm pulling back f by g, right? And so I think of what g has. And I just look at like what g is defined to be. And I look here and say, okay, well, this is the x component for g. This is the y component. This is z. And I know that f is, for us, just
Oh.
z, right?
Oh, yeah.
So just plug this in.
Yeah.
And that's it.
Oh, nice.
Yes. So there's another way to characterize this stuff in terms of the metric, but it's like, trying to think. Because the notion of integrating a function on a submanifold is like not exactly what you're really doing when you integrate stuff. When you integrate stuff, you're integrating differential forms of the same dimension that, you're integrating them on their domain. And because they're differential forms defined on a particular domain, there's no submanifold to think of. You don't think of things of less domain. It's just like if you have a K form, you integrate on the K manifold. And here you have to actually project down using the metric by saying, okay, how do I do projections? Well, I use dot products. And you want to make sure that you have an orthonormal basis to talk about coordinates for that thing and all this stuff. And so, you have to actually have a metric. If you don't have a metric, you can't do integration on submanifolds by projecting down a differential form or something. Like you can't integrate a function on a submanifold. You can integrate on a submanifold that's a K-manifold with a differential K form, but you don't need a metric to do that. So this differential forms are more general, actually. You don't even need metrics.
I see. But in real world applications, it's always going to be some sort of metrics, right?
No. I will say this: every manifold that you construct that is a smooth manifold, so that you can do differential forms, it does admit a Riemannian metric. So it's nice. But it may be the case that you need to work without them in particular cases. In particular, if you're studying Hamiltonian mechanics, you may work in two settings. You may work with symplectic manifolds, which are even dimensional manifolds, so like 2, 4, so on. You may also work with contact manifolds, which are odd dimensional manifolds, like 1, 3, so on, usually 3 manifolds. When you're working with contact manifolds, you almost never use a metric. And so you actually end up working with differential forms almost exclusively, even doing integration with them. So there are times, like I say that you use these things in Hamiltonian mechanics, but contact geometry comes up in like thermodynamics and stuff. So if you're doing those kinds of calculations, you don't necessarily have a metric to work with picked out for you. But yeah, anytime you're doing relativity stuff, you're gonna have a pseudo-Riemannian metric to work with. So you can make use of those things.
I can't really relate with it because I've like never seen those things. So
Okay.
I will like only make a picture in my head when I'll see that.
Well, the thing that you do in contact geometry is that you have in R3. So in contact geometry, you need like a 3 or 5 or 1 or 7 manifold, something of odd dimension. So the standard way people are introduced to contact geometry is they look at 3 manifolds, and on 3 manifolds locally, everything looks like R3 because manifolds look like Rn for some n locally, and so a 3 manifold looks like R3, and there is only one type of contact form on R3. And the way you define things is this. So instead of having like a set with a topology in a pair, you have a manifold, a 3 manifold, and what's called a contact structure. And this contact structure is defined to be a plane field. So instead of a vector field on R3, it's a plane field. So at every point you have a plane. So it's a 2-dimensional subspace of the tangent space. And so we draw R3. This is X, Y, Z. And the only contact structure that exists on R3 up to isomorphism, or what they call contactomorphism, is this one. So it's the kernel. I'll explain what that means in just a second. I want to say I have this right. I don't think it matters which direction you go. It just kind of flips the orientation, maybe. dz plus x dy. Okay. So what does that mean? Well, it means the following. You pick out a particular point and you want to look at its tangent space. Let's say at 0. Okay, so its tangent space, if I blow this up, looks like another copy of R3. It's, we're living in R3, so the tangent space should be R3. So this is del z, del x, and del y.
Yep.
Now, this is a vector field of tangent vectors, and vector space, sorry, not vector field. And we think, okay, this is a function, a linear function on this. Namely, it looks like this as a matrix. So I should write kernel of, 0 for dx, x for dy, and then 1 for dz. And so what's the kernel of that? What, you have, so this should look like vectors, so a, b, c. And namely, a can be anything. So I should say this is equivalent to a being anything, b being maybe anything, and then c has to be negative bx. Okay. Now, in our case, we're looking at 0, so x is 0. And so it has to be a can be anything, b can be anything, and then the third component is 0. So there's nothing in the z direction. And so what that means is you can pick anything for the x and y components. So you get this flat plane, the xy plane. And so you have a plane that's just like that right there, locally. And then if you go this way, what is happening? Y is increasing, and so nothing changes, right? I mean, I know you have dy, but you don't have a y component that's changing. It's just the y direction. So you still have planes that are flat. The xy plane still here on this part on the y-axis. Namely, you also have the same thing happening on the z-axis. Because z is changing and none of your coefficient functions are changing. Okay. And then as you walk in the x direction, what's happening? Well, you suddenly need that you can pick anything for a and b for the most part. And then the third component, if x goes up, the z part, let's see. If x goes up to a positive number, then the z part, if b is positive, goes to negative. So if you walk out in this direction, the positive octant with x and y being positive,
Mhm.
then z needs to be negative. And so it tilts down, starts to rotate this way. And so you get these other planes that look like this. And then they eventually end up twisting all the way around
Oh,
in this direction. So on. So the idea here is if you take a surface in R3, any kind of surface at all, doesn't matter what you draw, whatever I just drew, right, there will be no open neighborhood of that surface with the subspace topology at all, except the MD neighborhoods. And that's not a neighborhood because it doesn't contain any point. So there'll be no open neighborhood that is tangent to the contact plane. So think of the tangent space of the surface. That will not be tangent to the contact planes on any open neighborhood. That's the definition of a contact structure.
oh,
So
I see.
this is useful in differential equations because you can think about like if you integrate some plane field, you can get like foliations of a space or something, and your integral surfaces will actually be surfaces. But here you can't even get integral surfaces at all. So this helps you. Like if you want to say in R3, if I have some integral plane, if I have some plane field, is it integrable? And the answer is if it's a contact structure, then no. And it doesn't make much sense to even think about the metric in this case. It's not very helpful. You just think
Oh,
like
yeah.
this is
Yeah.
topological.
Yeah, I can think now. Like, why is it useless?
So anytime your concern is more about transversality, being transverse or tangential, than it is about being orthogonal or tangential, or even orthogonal or linearly non-orthogonal or something. Orthogonality is more about metrics, and transversality is more about tangencies and looking at the topology with the differential forms. You can actually classify. You can classify whether something's tangent or transverse just using differential forms without even having a metric. So that's why this is nice.
Is all of this used in is topology generally used in fluids?
It's extremely well used in fluids, especially in bifurcation theory. So if you want to talk about the transition to turbulent flows or something, you're instantly thinking about topological spaces, like you're thinking about torus bifurcations.
Yeah, because
There's some details about numbers that you use, like metrics, particularly things like the multipliers of equilibria, if you're looking at bifurcation theory. But most of the analysis you do, besides just like calculating eigenvalues of the Jacobian of the flow, is in general just looking at the topology of the invariant manifolds in the phase space. Yeah, it's very much used.
and
Um,
okay, and in let me think of an example.
Sure.
I can't really think anything on top of my head, but in such a case where you just care about differential forms
yes.
and not really care about metric, but at the same time you have to consider a metric, like you want to study a metric in that space. I mean,
What do you mean?
I don't know how to put this formally.
Okay. So what we were doing up here, where we actually had to consider the metric, I at the end get something that doesn't care about a metric. You get a differential one form or two form,
Yes, that's true.
and at that point, I can throw away the notion of a metric and say, okay, let's integrate this thing, and I don't need to know a metric anymore. I only use that to get a form, and even without picking a differential, without picking a metric, this differential form still exists.
Yes,
So
that's true.
metric
now
is
I
only
see.
a tool.
Yeah.
And it says, how do you project a volume form on R3 down to a submanifold that's been embedded? And the embedding grants you a natural projection to use. So that's nice. Another thing is in differential equations, if you're ever doing, if you're using Lie groups to solve them, you're dealing with symmetries of the differential equations. And sometimes I would guess maybe in like equivariant differential equations or something, you would want to know about differential forms. Like it would make sense to have those constructions there. If you're dealing with integral equations, which are like differential equations, but they involve integrals, this situation is likely probably quite similar to when you're using Lie groups to solve differential equations, just in the opposite direction. So you would flow along these vector fields and compute Lie derivatives of the differential forms that are involved in the integrations that you end up doing. We'll talk at some point about doing Lie derivatives. I think probably when we do the Lie group stuff.
Is it gonna be part of this course itself, or?
Yeah, will be. So like the idea is like think you have an R2, like maybe a vector field or something, and you might think, okay, well, what if I want to flow something along this vector field? Well, it seems pretty obvious how you do this. You might flow it like if you start at this point, it might flow this way.
Yeah.
The vector fields are natural things you'd want to flow stuff on. You can imagine that if I had a function on this space, that I define something called take a time epsilon or time t or something, and call a capital T, capital phi of t, the map that flows you for t seconds along the vector field, starting at x. So you plug in x, and then you let it flow for t seconds. This is t, and then you get out the result, which is phi t of x. Okay, so you can flow a point, and it's just called phi t. And you might imagine that if you have a function f of x, right? I'm writing x when it should be a vector. F of x is like, f is a map from R2 to R. So it just spits out numbers when you plug in a point in the plane. You might actually imagine that there is a flowed version of f where you say, okay, what happens to f if I flow the points before I plug them in? So you might think, okay, we might define something called Lie, excuse me, not that. We might put f compose phi t. And this is, again, a map from R2 to R. Just think this is a map from R2 to R2. It just takes a point and maps it along the flow t seconds later. And then you might take shorter flows. You might let t be smaller and smaller, right? So just flow for a third of the time. This is a new t. Then take a smaller one. And you can imagine that I get different flows every time. So this is t prime prime. So for each of these, you get a different flow map. T prime, t prime prime, and so on. And you can keep going smaller and smaller, and you can define this thing. L, and imagine the vector field is v, right? I would write sub v for all these flows just to denote that I'm flowing along v. So L sub v of a function f is equal to the limit as t goes to 0 of f of phi, let me write it this way, f of phi sub v of t of the point x, I should plug in x here, minus f x over t. So this is called the Lie derivative of f with respect to v. So I can actually differentiate functions with respect to vector fields now.
Oh, that's not like that. Kind of too abstract. I was thinking like some weird thing.
Right.
Like, that's kind of obvious. I mean,
Yep. But this works not only for functions, but you can actually Lie differentiate. You can Lie differentiate differential forms. And nicely, the formula is very similar to this for that, the way you define it. But Cartan came up with this nice formula called Cartan's magic formula, and it looks like this. And it's very easy to compute things this way. What is this? This iota v thing, like that's a little bit weird. Well, the idea is this. Think of what d omega is. So if omega is like a one form, so omega maybe is like a one form. It could be anything. It could be a k form. On m or R2, let's say. Then it looks like omega equals maybe alpha of xy dx plus beta of xy dy. Right, that's a generic one form on R2. And well, what does d omega look like then? Well, it looks like this. It looks like negative alpha sub y dx wedge dy. I have to anti-commute because I would have had dy wedge dx to start with, plus beta sub x dx sub wedge dy. So I can rewrite to simplify a little bit. Negative alpha y plus beta x dx wedge dy is what d omega is. And so now what is this thing? Well, this is a two form, d omega is.
Yeah.
on R2. Oops, 2, 4. So namely, I can plug in two vector fields into, I should say U and V, into d omega, and I get some result. Well, this is called the left contraction of d omega, and instead of being a 2 form like omega, d omega is, it's a 1 form again. And the way it works is this: if I plug in, let me write VU in this case, just to keep it straight. If I do this, this is a 1 form, so I can plug in one vector field. You just stick V in the left component of d omega. Oops. D omega V W, or U, sorry. So it just stuffs V into the left part of that.
Oh, okay.
And this is very easy to calculate, always. And this works for any differential form, no matter what grade it is. This formula is awesome. That's like a super huge workhorse in differential geometry.
Did Cartan name it as like Cartan's magic formula, or just like?
I don't think he did. I don't know. I have to actually read his original writing, but he wrote in French, so I don't. Maybe he did.
Oh.
French people read shit like that. Yeah. But this is like, I mean, this allowed me to solve like half my homework problems last month.
Wow.
It's super useful. And it's hard to visualize what exactly is going on there, but with some effort, you can do it. The intuition for this comes better from this, actually, like from looking at the limit version.
Yeah.
It's a little clearer. But yeah, the idea is you're flowing the domain of the differential form.
Yeah.
Like you're flowing the neighborhood of a point before you evaluate the differential form on the tangent vectors to it. So it's
As soon as you like started talking about the flow trajectory, I thought this thing, like if I was given a task to like write some kind of like formula that
Yeah.
of the trajectory. So I was thinking like considering the vector field as a flow and like putting a particle in there
Uh-huh.
and then like letting it go for a very short period of time,
Mhm.
and then starting that particle again from zero velocity from that small displacement, and then so on. So it's gonna give you the trajectory. I mean, it's like this is the obvious thing to do. I mean, it was kind of natural. I was thinking of something as like very abstract.
Oh no, there is a really nice thing. Nobody writes this, I'll say. After you have learned about Lie groups, nobody writes this thing anymore. The flow map.
Okay.
They write it this way. They actually define the following thing. Exponent T V, the vector field, you plug in X, is defined to be the flow map for T seconds along the vector field V of X.
Okay.
And then this thing is a diffeomorphism of the manifold that you're flowing along. Like it's a map from it to itself. And you can differentiate this. And some people write it this way. And in fact, you can actually differentiate this with respect to t, and you would not believe what it's going to be. So the derivative with respect to t at t equals 0 of ETV x is equal to this thing. V applied to ETV x at t equals 0. Sorry. Or sorry, you don't put an x here. You just put in this. So the derivative of a flow is the vector field.
Okay.
And it works out with the standard like calculus notation. So,
Oh, wow.
So actually, these turn out to be elements of Lie algebras. Vector fields end up being elements of a Lie algebra. So you say this is in little German G. I can't draw that right. And this thing is in a Lie group G. And when you differentiate a Lie group's elements, you get, or when you differentiate a Lie group, you get Lie algebras. And you can integrate those Lie algebras by exponentiating them. And you get this nice stuff. So this actually gives us a whole new toolkit that we can use to solve differential equations. And it works for like every differential equation, no matter what. PDEs, everything.
Cool. And it doesn't seem like there's a lot of like stuff to learn in Lie from this point, or is it
No,
like
there's not.
not right?
No, there's a pretty difficult idea to like visualize the first time you see it called diffieties, spelled like this. There's two things that I haven't really showed you. So a diffiety is like the differential algebraic geometry, or excuse me, the algebra differential version of an affine variety from algebraic geometry. which is like the zero sets of polynomials, but this is the zero of a differential equation.
Okay.
And then there's also a thing called bit bundles or prolongations. And once you have these two, you can solve differential equations.
You mentioned jet bundles in your lectures, right? One of the lectures.
Maybe. I don't remember for sure. I know I mentioned tensor bundles, but maybe not jet bundles.
I've seen jet bundles written somewhere.
Probably my name on the sheafification Discord.
Oh, probably.
But yeah, those are the two objects that you need. And these are both due to a guy named Charles Erasmus. But he was really prolific and kind of brought the theory of bundles to physicists.
See.
But yeah, let me see if there's any more exercises we can do while I'm still recording, and then we'll go ahead and end it after that.
Actually, like the dining hall is about to close in 8 minutes, so I have to go and get some food right now.
Okay, see you.
Okay, see you. Thank you.
Let's see. Did we do everything? We did 11. That's recalculating the integral with polar coordinates. We did all the pullbacks exercises. And we did not do 13. That one is kind of tedious. I don't want to have to pull up Green's theorem and stuff. And then I think there's one more, 14. Okay, we can't do that one. So I said before that if you have a function f on R3 and it's smooth, you can calculate the gradient of it, but df should act like the gradient of it. So d of a differential 0 form should be a gradient, d of a differential 1 form should be something like a curl of a vector field, and d of differential 2 form by Hodge duality should be something like the divergence of a vector field. And I say by Hodge duality because you can translate by the Hodge star between 2 and 1 forms in R3 because 3 minus 2 is 1 and 3 minus 1 is 2. So the Hodge star takes you back and forth between 1 and 2 forms in R3. Okay. So namely, I should write d omega 0. This is the gradient. D omega 1 is like a curl. And d omega 2 is like a divergence. Okay. So df, namely f, is actually a function on R3. So df for us is f sub x dx plus f sub y dy plus f sub z dz. Or if you like matrix notation, it's fx, fy, fz. Okay. If you have a differential 1 form alpha, then d alpha is going to have been d of bx dx plus phi dy plus phi z dz. Now, the easiest way to calculate this thing is to think about what the basis components are going to be. So I have a 1 form, so I should get a 2 form. So I should end up getting dx wedge dy, dx wedge dz, and then finally dy d wedge dz. Okay. So I should pull this over here a little bit more. Now, dx and wedge dz is going to be this thing I differentiate with respect to z, but then I'll get dz wedge dx, so I need to anti-commute it. So it should be negative phi x sub z. And then finally, phi z sub x should just work out naturally, so I don't need to do anything fancy. So no minus. All right. Then you have plus. Well, I should have differentiate the zth one with respect to x, should give me dx on the left. Okay. And I'm being stupid here. That should have been these, actually. So let's go this way. I was mistaking this for a z. That should be y. This should be commuted. So I want to do y with respect to x minus x with respect to y. And then finally plus z with respect to y minus y with respect to z. Okay, so that's the exterior derivative of a 1 form. So why does this act like a curl? Well, it's because if I hot star this, this is going to be dz, this one's going to be negative dy, and this one's going to be dx. And so if I, if I do that, I get three components, namely z or dz, negative dy, and dx, and then I can take the sharp of that, and it'll give me a vector, right? So I'd have del z, negative del y, and del x for my basis component, or my basis vectors. Now, thirdly, if I start with a differential two form, which is d omega. Omega is the two form, and I exterior differentiate it, end up getting the exterior derivative of xi z dx wedge dy plus xi y dx wedge dz plus xi x dy wedge dz. Now you can imagine that I should get a differential three form. So this should be, well, I'm going to get xi z sub z dz wedge dx wedge dy. Now I commute twice, so putting dz to the right twice is going to leave this positive. Okay. Now I have xy. I want to differentiate that with respect to y, and then commute it once, so I should get minus xy y, and then finally another plus xy xx dx wedge dy wedge dz. Okay. Now that's it. That's all of d omega. And if I hot star this, I get a zero form, which is a function, and it's going to act like, let's see, a divergence, right? So effectively, this is the divergence of a vector field. Namely, I should say this. I want to say that this is the case. I need to double check, but the divergence of xi, yes, this is actually right. Xi x del x plus xi y, that should be a minus, I'm sorry, del y plus xi z del z equals this. Yep. That's the divergence of that. So really, if I wanted to do this proper, I should have written this commuted, anti-commuted, and it would have given me the right thing. Namely, I would want to flat this and then hot star it to get the appropriate vector field that I can. Namely, what I'm saying is div v. Well, I need to turn this into a differential one form. I flat that and star it. Now that's a two form. And then I exterior differentiate this. And then I have a three form, and I hot star it, and I have a zero form, and that's it. So almost done. And I think that's all actually. It was the one last exercise that I didn't stop covering, which was 13, but that one's more annoying. I don't like even looking at the old Stokes theorem. It's so much more ugly. Okay, I'm gonna go ahead and end it. And we'll start on the groups. Okay.